do a version not described on the TensorFlow web page, because sometimes that's just how it is. But eventually I did get that working. Whether we need that tonight or not, we'll see. What we're going to be working on tonight is a setup to try to determine what digits is placed in an image. Except when I said digit, I mean plural. What digits are in an image when they're all smacked on top of each other? This is going to sound kind of strange. So I want to show you what I'm getting at. Now, this whole episode is just going to be getting the data set ready for that kind of operation. So I fully expect to kind of take the whole time doing that. So if we open our previous... Where am I now? Oh my goodness. Let me kill this. TF, new TF, that's what it is. Doink, there it is. Okay. I gotta grab some old data before I do this. As always, new TF, this one. Because in this old file, I'll grab this stuff. Hopefully this works. Yeah. We might not even need TensorFlow, but I want to grab my data. Where's my data? There we go. Dataset load MNIST. That's the thing I needed. We don't even really need the GPU working for that, but we want this to work, so we'll do all this nonsense. What we're going to do here is load this MNIST dataset, this training data, whatever, and we're going to make a new dataset from this. Pipeline as PLT, right? And we'll do plt.ion, of course. Because this dataset, you might recall, looks like a bunch of things, probably like this. Can I get away with this? Does this work? I bet that works. Nope. Does not work. What is train.shape? What is train in this context? Right. Right. Train of 0, 0, perhaps. 0, 0. 0. There we go. There we go. You get images that look like this, right? Where there's a single image, like this is a 5. What we're going to do is create images that have multiple digits, all on top of each other. So that might not be clear what I'm getting at, so let me show you in a very quick example. What I mean is, we're going to do something like this. Take one image, add it to another image, and then we will divide the whole thing by 2. Right, so take the average of 2 images, say. Oh no, what have I done? That's not exactly what I want to do. Do this, and I'll make a new figure. Could use subfigure for this, but I don't really want to do that. I like having total control. There we go. So now we have 2 figures here. Let me put them the other way here. So you see there's a single one, that's a 5 clearly. This one is a 5 combined with a 0, I believe. We can actually double check that. And we would want some model to report both 5 and 0, just the integer, hypothetically speaking. You could envision a more challenging model that just tries to rip out, that takes, given this image, tries to produce the image that looks like a 5 and the image that looks like a 0. That would be an alternative kind of image you could construct. But that's not a super big deal. So that's what we want to do. This entails doing a couple different things. With normal sort of MNIST, that's what this data set is, of course, you have a multi-class classification problem. Each image is only one thing. In this situation, however, each image can be up to 10 different things, right? How many different labels might we bang together? So that is no longer just a classification problem, that's like a tagging problem. And actually, we should open up our browser and take a look-see at that kind of problem. Yes, browser. The tagging problem. Tagging classification. It's not a classification, right? But that's what I'm going to put in order to get multi-label classification. See, Wikipedia, boom. Right, because things can have multiple classes, because there could be a 1, there could be a 2, there could be 3 there. There could be all 3 of those things. We mashed together 3 images. There's a couple different ways you can go about this. Here's a simple one. Transformation into binary classification problem. Essentially, you make a little binary classifier for each possible class. So this is a thing we can do. That's pretty straightforward, I think. 1. Turn into a multi-class classification problem. This is not going to work in our situation. Here, every possible combination becomes its own possible output classification. But of course, this thing's going to be highly correlated. If you had a 1, a 2, and a 3, well, that's strongly correlated with just having a 2 and a 3. So really, you'd have to build this very carefully. Probably not just a standard like categorical cross entropy loss or like logistic regression kind of thing. You would want to build a nested logistic regression, like nested Loj model is what it's called. I fussed around with those a little bit in grad school. But those help you when your classes are correlated in some way. In this context, though, it's like a tree of correlation. It's like, well, clearly this is correlated with this, but also with this other thing. And it's not even a tree. It's like just a weird arbitrary graph of correlation. So it gets kind of goofy. Stream classification, we're probably not going to worry about that. So what we're probably going to do, just to get something simple, is this straight binary classification. So again, it's like you're building 10 models of does it have a 1, does it have a 2, does it have a 3, so on and so forth. That's not one. Terminal, there we go, perfect. Let me do plot.clf, close all figures, right? Yeah, oh no, it didn't close all figures, it just clears the figures, whoops. I guess plot.close, all. There we go, perfect. Make sure I do that, plot.close, all. Put that in my code just so I have that for later. Okay, so that's what we need to do tonight to make that data set. Right now, we've got our input images here, like train 0, and our targets, our training Y sort of data, is train 1. These are all, of course, the labels, right? Oh, come on. There we go. These are our integer labels. First one's a 5, second one's a 0, then a 4, so on and so forth. And you can turn that into a categorical thing, relatively straightforward. The kind of data we're going to end up generating, a given label in a traditional classification problem is going to have a bunch of zeros, followed by like a 1 for whatever class it actually is. Right. What we're going to have, however, is going to be a bunch of different ones for wherever it happens to be. Whatever class it is. It's like, okay, 0, 1, this is a 2, not a 3, not a 4, is a 5, not a 6, is a 7, so on and so forth. So we're going to want a function that randomly chooses combinations. I think I want to start with up to 2, maybe even 0, maybe more, well, no, who knows, of our training data set, and then creates a new data set from that. This is going to be a harder problem, of course, as you can imagine, because like there's a 5 and a 0 here. Like, how are you supposed to tell? And like, if you had a 9 in here, like there could be a 9 in here, you wouldn't know anymore. You'd have no way of telling. So we expect it to be hard. We don't expect to do perfectly. That's okay. We go after hard problems to sort of understand things. If we only solve easy problems, we're not really going to learn anything. You'll train a network to learn anything, but you'll end up learning nothing. And that's even less valuable. So we need to randomly pick 2 sets of 2 of these images, ideally that have different labels, right? If you put together a 5 and a 5, well, you know, that's, you can't, you say 5 twice, like, okay, it's even more of a 5. For example, if I say tx of where ty equals 5, these are all my 5s, right? 5s. You ever watch Clone Wars? You know, there's the one clone who's just named 5s because his identifier was like 55555. Yeah. So that guy, he wants to do his little digit recognition problem. If I take this image over here, except we're not using train anymore, now we're using 5s, and we don't need to grab that because we already have that. So if I look at the first two 5s and average those together, right? These are both 5s. But like one 5 clearly different from the other 5. What should the model report here? It might look like one is on top of the other, but that's not really true. They're just average. One might be darker than the other, and then it does tend to take more emphasis, but that's just the way it is. And you could do other things rather than averaging. You could straight add. That would look different. Or maybe it doesn't look that different. I thought it would. Oh well. But yes, that's an example of that. Let me grab this, dump that down there. Continue on down. So, given 2 for images, we'll turn this into a function, but first I just want to do a thing first. And you have image 1, index 1, there we go, equals, 0. Index 2 equals 1. Like, obviously, later we will fix this. If if they are the same number, I don't really want to deal with that. So index 2, we're sort of going to like pass, continue through some kind of error. I am going to go ahead and say continue. Right, this is going to be in a while loop. We'll say raise value error. Labels must be different. Maybe we'll put it in a try except block, whatever. Labels must be different. We'll just do that. Supposing that your labels are different, I want you to grab the actual value at index 1. We'll just say numpy.mean, right? Right, numpy.mean. A is an array. Turn the average of array elements along a given axis. So you gotta futz around with that. Right. So if I have... So I need to sort of make a new array of that. So if I said tx of index 1... Hang on. If I pass in a list, I think you can do this, index 2. Oh, except I haven't defined index 1 and 2. Back up here. There we go. I think you can do this. You can. I love America. This is so good. You asked about the shape of this. I got 2 things, 28 by 28. I want to take the mean along the first axis of those things. So, of tx of, let's say, I for I in, I think you just say indices, right? I think we can just go with that. X is equals 0. And I will say indices. Right, we'll make this a little more general in case we want to support up to 3 digits slapped on top of each other at once. Just for now, we'll do this. Just for now, we need to change this bit now. Now we're not checking one thing, we're checking a bunch of things. So if I want to say set of, hang on, ty of I for I in indices. So what are all the, this is computing, what are all the labels that we're looking at, right? Set just says give me all the unique labels. If the set, the length of the set, hang on, if the length of that set is less than the length of indices, we're in a bad time, right? That's a real bad time. Then this bad. Labels must all be unique. All be unique. There we go. Update this a little bit. Perfect. And we'll put in indices here. Just so someone could see, oh, I didn't mean to do that. Sure, let me give you that. Whatever. But now we can just grab that arbitrarily. Right? This should be, excuse me, properly speaking, index 1, index 1, index 2, whatever. Whatever we're dealing with, indices, right? Cool. We prove that this is functional. Yeah, so did not raise an error. That's good. Don't like how... Oh, because I need to go turn off my auto indent. And then should be able to do this. And that's just, oh boy. I don't know why that got so big. Oh, because they're floats now. That's fine. That's... I don't care. That's not a big deal at all. Can I, like, not make that not happen? Can I change the D type? D-type, D-type. Try to use and compute the mean. Integer inputs, the default is plus 64. Floating point inputs the same as input. D-type. Alright, actually let's do that. Say D-type equals uint 8. I don't know. Uint 8, because that's how they're stored, right? Pretty sure that's how they're stored. Tx.shape? No, tx.dtype. Yeah, uint 8. So now you look at it, it rounds all those off, which is fine. We don't care about that. That is not a big deal at all. Okay. So that's what you're going to say, you're like adjusted your new label or whatever. New image. What is this? New label. This is going to be, right, numpy.0s essentially. We might futz around with this a little bit. Of size 10. Right, dtype equals numpy.uint8. Again, we might fix that later. And then we say new label of indices. Oh, shoot. We gotta fix this. We'll fix this in a second. Equals 1. So we'll set those tags. That's what this is doing, setting the tags. We sort of create an object, and then we set the tags. There's a problem over here. I'm using indices, which is just a... Is that which index I'm doing? Which? Oh, okay. No, hang on. Hang on a second. I gotta get this. I was backwards. Indices is not the thing we want to set labels in. We want to set the labels with, hey, whatever the actual labels are, right? All these guys. We already verified they're unique, so we're not going to be like double setting anything. This will be just fine. So that should be okay. Tell you what, we got index 1, index 2 set up. Let's run this code, see what happens. Oh, look at that. Didn't blow up on our face. Got some new image. Let's take a look at that. Plot that image show. New image. There we go. Yeah, there's our 5 and 0 put together. Perfect. And our new label is this. So it contains a 0. And 1, 2, 3, 4, 5. Perfect. So that should be okay. I might have to futz around the data types. Like maybe this doesn't want to be uint8. Maybe we'll have to make it a float because it's going to go into some other computation, whatever. But that is what it is. So that's like for a single guy, right? So we want to do this in a function. And really we want to do this. We want to do this on the fly in a reasonably quick, not on the fly. I want to make a big data set and do this all the time. So def, I don't know, we'll make a data point, or com images, combine images, right? And then it'll be whatever indices I'm dealing with. And I think that's it. Right? I feel like that's the only thing that I gotta worry about. And you just gotta check these kind of things. Oh no. Do that. Yep. So that looks like that. And you know what? We'll just return right here. Not even do that. You'll notice like, oh, I'm not returning the labels. We'll do the labels separately. Now these labels are pretty easy. I have a feeling that what I'm going to do is I'm going to say number of, I don't know, in data, whatever. How many images do we want to generate of this fashion? I don't know, 1 million? Is that enough? I don't know. To the 16? How many are in MNIST? 60,000 in MNIST. So if it's a 2 to the 16, that's close to that many. So a similar amount of data. Images in the end overall, but like it's a more challenging problem. So how well can you do? We'll do that. We'll start there, just to not destroy my machine or anything like that. So we want to make that many data points. Okay. This is for a single set of indices. Combine them up. So you could imagine you want to choose a bunch of sets of indices. So let me make all these indices first. Actually, does it have? Can I just choose? Oh, no, I need to choose the actual indices itself, though. You can take a random sample from a 1D array, but I need those indices themselves because I need to grab the labels and the images separately. So what we need to do is all index. This is just going to be an NumPy.aRange of length of, what is it, tx? Yeah, sure. Length of tx, dtype equals numpy.int. Int's fine. No, uint, whatever. That's probably uint 32. Uint 64 even. Oh man, I don't need that. Truth be told, I really only need 16 bits. Yeah. Because this number, the biggest one I have, is less than 2 to the 16 minus 1. Dunk. A little bit of room. We'll do that. We need to randomly choose from this set so that we can grab the correct images and the correct labels. Okay. So if you were doing something kind of dumb, hypothetically speaking, like, no, these are my images. We'll make an empty array. My labels, make an empty array. We'll start with the dumb thing, because that usually works better. Not that the dumb thing is better, but starting there and improving usually gives you a better product in the end than trying to start with a smart thing. Unless you already know what you're doing. If you already know what you're doing, then, you know, it's not smart or dumb thing. That just is the thing. So for I in range in data, this many data points, right? I need to first generate a pair of images. numpy.random.choice, right? We were just looking at that. numpy.random.choice. Generates a random sample from a given 1D array. Okay, interesting. Size, int or tuple events, optional. Oh. So actually what I think we're going to do, do this. Choices equals numpy. And we'll just only do pairs of images for now. numpy.random.choice. Right? And we're going to make a choice from all index. Size is going to be, how many of these things do I want? I want n data of them, right? How many do I want in each slice? I want 2 of them. And I will say replace equals false. Oh, that's going to burn me. No, I have to have replace equals true. I can't say replace equals false because I don't have that many images, right? That would be problematic. Unless, no, that's just dumb. What is P? Probability associated entry. No, that's fine. So there is some randomness, right? But there's a 10% chance, roughly speaking, that a data point will have the same, 2 of the same index. And so we're not going to be able to get as much as we would have liked with this. That's fine. I'll just generate twice as much data. And I hope that in the end I'll have enough. Yeah, it's not perfect, but I think that's probably going to be good enough. And if we have problems with that, we'll deal with that when we get there. Shouldn't be a big deal. We can always futz with this. Futz with this thing anyway. And I should say, like, wow. What do I want to say? While I less than n data? Yeah, sure. There we go. I equals 0. Which iteration are we on? So we're doing a while loop because some of these choices are going to be hot garbage. Because what we're going to do is we're going to try, and we're going to try combine image. Oh, I didn't actually even test that. That's funny. Combine images of indices. Does that work actually? Did not define. Of course. Of course I haven't defined that. Why would I define that? That's silly. Yeah, okay, it seems to work. It does something. Yeah, that's about what we expect. Sure. Sure. Combine images of what are our indices? Our indices are choices of I. Right? That's the particular choice we're trying out. I want to say my current image is equal to this, except if there's a value error, we are just going to continue. Which continue means go to the next iteration of the loop, don't do the stuff in the rest of this loop. That stuff in the rest of the loop being this stuff. Hey, what do you know? This thing. And what I'm really going to do is I'm going to make labels right here, where I make labels be the size of n data, hang on, n data of them and 10 across, right? N data is not defined. Of course not. Why would it be defined? That's silly. Labels. A starts off all zeros. We're going to be filling it out over time. So I don't need this anymore. I just need this. Boom. Yes, this is made with TY. That's fine. Really, I want to shove in TX and TY into here because eventually I'll be using different things. So TX, TY, perfect. When you redefine this, there we go. Good. So this creates our image in question. What will we do? Well, let's, instead of making our images an empty list, let's say numpy.zeros of, again, n data 28 dtype equals numpy.uint8. There we go. This is a lot of memory right there. Right? Oh, I only needed to do half as many. Hang on. No, I should do this the other way around. 16 there. But when I generate my choices, I should generate twice as many there. That's the smart thing to do. Rather than have to keep dividing by 2 everywhere. Let's do that. Okay. Labels.shape, which takes up almost no space. Images.shape, that takes up, some space. Right? Each one of these is a byte times this times this. So you said numpy.product of this. Each one of those is 1 byte in your computer. This is how many bytes you're taking up. You're thinking, that's a lot of bytes. I mean, it's like 50K. Excuse me, 50 megs. 50 megabytes. So depending on what era you live in, that could be a lot or low. I'm tragically low on water, but that's okay. Okay, that's great. So what we're going to do then is... Actually, we could do this right here. I don't even need to save this off to a temporary variable. I can just do ims of I is equal to this. And then the all-important step is say I plus equals 1. Right? Need to do that. There's one thing, however. Oh, hang on. Where are you host? I need another iterator in my choices. Yeah, I need a choice iterator that's going to go faster than all these other things. J plus equals 1. J equals 0. J plus equals 1. Right. And here, I need to pull out the jth guy, because there's going to be some guys that are garbage, and that's going to go faster, in a sense, than this I iterator. We need to make sure to increment that when there's a problem. Or if everything works great, that's fine, also carry on. Either way, we need to increment that to grab something new. And we will want an extra check that says, if j is greater than n data times then length of choices, whatever. Greater than or equal to, right? Because that's the last thing. Then we are going to break, but we'll print warning. No, we will use like warnings. Import warning, right? Warnings, plural. Yeah. Warnings.warn is the thing. There we go. Cool. Warnings.warn. Less data than desired. We will say j being the number of things that we get. No, we got I things here. There we go. I admit I didn't like this printing syntax at first with this F strings, but I really do like them. They come in handy. So useful. Up here. Import warnings. Cool. Now we got that. Alright. Should generate a bunch of data for us then. Now let's see where this went wrong. Oh my. Oh, I didn't. It's not wrong, but I didn't print out any, nice. Anything nice. Right. I just say if I mod in data divided by 100, whatever. If that equals 0, all right. Now I want to print. Let's print a little x to show that we're getting somewhere. We'll print a little dot actually. End equals nothing. And we'll print just an empty new line right here. Let me do all that again since that took almost no time. So now we should start seeing. Oh, I gotta flush, of course. Of course I gotta flush. Ugh, man. Alright. After we flush, it's not print, it's not OS. No, there's not an OS. There's like sys, I think. I'll look this up if I don't remember. Sys.flush standard out. Flush. There we go. That's what we need. Import sys. Right? Come back down here. After you print this, we will say no, flush the standard out. I know it's going to take some time, but I don't care. Dot flush. And we won't do this every 100 because it's really pretty quick. We'll do it every 10. Yes. So every 10% of the way, we'll get a little tick. There we go. And you can see that going there at the bottom. Just a little mini progress bar because I didn't feel like running TQDM. Okay, boom. Now we have a data set. Great. And we didn't get our warning, so I think it was good. What was J versus I? Yeah, that's about 10% bigger, right? To be expected if about 10% of the data points were bad, right? This times 1.1, lo and behold, to within 1,000. And that's assuming the distribution is perfectly even, which is not. But that's super cool. In fact, if you look at plot.histogram, plot.hist of ty, it's not even. There's a lot more ones. And a lot less, is this 5? That's weird. A lot less 5s. Why less 5s? I don't know. That is perplexing to me. A few more 7s. It's something about, these are cover mailing addresses, so maybe it has to do with the distribution of zip codes, or the distribution of street addresses, which somebody might be like a law of large numbers things. I would have expected 0 to be a little smaller, actually, in that case. Since 0 is never going to start like a street number address. But I think 0 does start zip codes, so that's all fine. Oh well, anyway, things like that. Mostly even. But this weirdness going on here, this weirdness. So not a perfectly even distribution, but you could use this, generate the same thing, get your confidence intervals for how much space you will think you're going to need. And in my situation, I wasn't worried about it, since I knew I could just generate twice as much, or you can always generate these choices on the fly. Doesn't really matter. In fact, let's change the code to do that. Why? There's no reason to store around these choices. That's dumb. So in fact, let's fix it. Let's fix it. We generate our choices on the fly. We'll say choice equals numpy.random.choice. It might be nominally a little bit slower, but it's not a big deal. We want size equals 2, and now we can say replace equals false. We definitely want not the same index twice, because that will obviously be the same label as well. Numpy.random.choice. Replace equals false. Yes. Okay, good. Good. So that's our choice. We don't need this warning anymore. I can go away. We might end up with the exact same choice of 2 variables that we had before. That's a possibility. And I'm going to deal with that in a second. I'm going to say pass choices. Yeah, choices now becomes a set. Right? There we go. Get rid of that. Set, an empty set. What we will do, not choices, but this guy right here. Oh no, what have I done? I've done something terrible here. This needs to be choice. All the data I made is wrong. I used the fixed indices thing rather than labels, which should have been, rather than choice, which should have been changing. Take a look at new label. 0. New label 1. What the fuck is this? Oh, that wasn't even changing the right thing. So many things. Labels of this thing. Alright, so, you know, we had to fix our data anyway, so we might as well fix it more. We're going to generate choices on the fly, so that we know we generate enough data. We don't even have to think about it. We'll just generate exactly as many choices as we require. Great. There's just one problem. What we want to do... what we want to do is say, if... Let me think about this. Set of choice, can I do that? If A equals numpy.array of, I don't know, 0, 1, whatever it is, doesn't matter. 1. What does a set of this look like? Okay, good. Would it try to create a set of the whole array, or each element in the array becomes a set object, which is what I wanted. If set of choice dot is subset. Can I just say in choices? I think I can do that. That's bad. So what I want to do is say choice equals set, maybe? Do this here. And I'll say while choice in choices. While it's something that we've already seen before. Generate a new choice. Right. And I don't need this J anymore. But I'll say is max iter equals, I don't know, try no more than 1,000 times, whatever. J equals 0, J plus equals 1. And then it'll say if J greater than max iter, hey, greater than equal, I guess. Doesn't really matter in this context. Now is when we like warnings.warn, like we're done. Oh, I need like a double break though. No. There's a way to do that. We'll yeah, we'll do that actually in a second here. In the unlikely event that this happens, we will raise bad time. Yeah, bad time, we'll call it can't get enough choices. Can't generate enough data. Right, there's just not, we've tried too many choices, maybe our initial data set's too small, whatever. Why are we raising here? Because like this is a problem, like we can't fix this issue. You might say, well, we can just accept the data that we have, and that's exactly what we're going to do. We will accept that. That is what it is. But what we're going to do, bad time is a, is this like an iteration error thing? No, okay. Well, fine. I will create a custom class here. We will say class bad time inherits from exception, right? And it does nothing. Does nothing at all. But this will let us generate a custom error. And what we can do is we can say try this whole thing. Like it's not the end of the universe that this happens. Like we have some data, except bad time. I don't know. Yeah, whatever. Except bad time. Actually, I don't even want to like pass a thing here, right? I just want to say here, warnings.warn could not generate enough data. Wanted. How much did we want? We wanted n data, right? N data, right? Got. We only got where we're up to I, right? So that's a problem. Cool. But that's fine. I mean, whatever. It is what it is. We will just accept that that is how much data we have, and we will say that images is now equal to images up to I, and labels is equal to labels up to I. Up to I. There we go. Oh boy. Getting busy here. Let's make our bad time. Let's go here, see if I crash my, no, okay. I wasn't happy about something. Indices. Oh, I didn't turn on my Python debugger. This thing, Python debugger is so cool. Like it drops you into your problem location, and now you can look around and like, what's going on? Why? Oh, because indices is a set. Because it's not what I wanted at all. Choice in choices. Oh, here's a stupid question. What is choices? Yeah? What's choice? Choice in choices? Yeah, no, that's dumb. What I really want is choice dot is subset choices, which is totally true. Yeah, okay. I thought in would work, do that for me, but need to be a little more clear here. So if it's a subset, if it's one we've already chosen, then pick a new one. But there's another problem here. Because choice is this thing, right? Set, bonk, bonk, of that. If we get out of that, then say choice equals not by, I don't know, this is a list of whatever it is. Then we don't care. And it's fine. And now we have a list of all our choices. Great. Okay, now it's going. And you see, sometimes it's a little faster, sometimes a little slower. It's got to skip a few here. This will ensure that we have all different choices. Now we can look at those choices too. If we really, oh, I made a mistake. Choices is empty because I forgot to add things to the choices in the event that we found one we liked. So I need to say choices.add. No, not add. Update, right? Set.update. Says the union of itself and others. Choices.update. Choice.update. Choice. Perfect. Get that going. Now we'll actually check. Got it. That's good. All right. So the little dots are going. Our little poor man's progress bar. Always a very, very good time. And again, if you have any questions, please feel free. Drop a line in the chat. Send me an email. Leave a comment. Whatever. Here it's complaining. This is surprising to me, actually. This is very surprising. Because I know that there's, there's 60,000 choose two combinations that I can make. I'm pretty sure I can get the ones that I want. You're saying we only got 40K. I am highly suspicious of this. Highly, highly suspicious. These are all my indices. Yeah, okay, great. Sure. Wait, what? That's... Oh! I see the problem. I'm actually surprised the guys many that did. I'm adding 2 numbers to this every time. Right? But really, I just want to make sure I don't use the exact same pair. Right? Because if I use 2 numbers every time, I can only ever get half as many numbers as I have. Otherwise, I'll have a real bad time. Right? And that's exactly what's happened here. Right? That's where you get that. I'm actually not sure how I get as many. How I is as big as it is. That's somewhat surprising to me there. I don't think that's correct. Maybe I didn't reset I. No, there's I. That's very strange. Very, very, very strange there. I ought to be this number, right? As many things as I have in choices divided by 2 ought to be this. And how do I have half of a thing? That is very curious. Anyway, choices needs to be a set of sets, essentially. So I did want to do this. If choice in choices, I was right the first time. And I want to update, I want to add, right? Then it's a set of sets. So if I get the exact same pair, that's bad. I don't want that. But as long as the pair is different, then it's okay. No, it's not. Unhashable type set. Okay, excuse me. I want a frozen set. Or I want a tuple. Whatever. Yeah, I want a tuple. Oh, snark and dark. Yeah, tuple. There. Tuple. Or do I put this twice? Oh, isn't there a do while? I gotta double check. I need a do while loop. I always do the first one. Python do while. Could have sworn that was a thing you could do. Maybe not. Blah, 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 blah. This takes forever to load. Come on, come on. Of course, I'm streaming a bunch of videos, so that's probably why. All right, never forget it. We'll continue with this. This is fine. Unhashable typeset. I don't want it to be a set. I want it to be a tuple. There we go. Tuples are immutable. Once you make a tuple, you're not allowed to change it. Oh, no. Yeah. Don't try to run a bunch of code inside the Python debugger. Invalid value counter to true divide? Mean of empty slice. I don't know what you're complaining about. That's ridiculous. It's fine. Everything's fine. Choices. Length of choices. Should be... Yep, okay. Again, that's about as much data as we expected to create. Because that divided by our 60K. It's a little bit more than we expected because I was also demanding that they be unique. And the distribution is not perfect. And the further the distribution is from uniform, the more biased it's going to tend to be, even in this context. But, what is I? I is 2 to the 16. Perfect. Oh, right. 2 to the 16 times 1. Yeah, there you go. Again. I had to do, like 700 extra. Got 1% more than I predicted. But again, that's probably related to the distribution itself. That they come up a little bit, the repeats come up a little more often than I expect. But now every pair of data points is different. I got all these images, I got all these images, I got all these images like this. Great. Let's just verify that some of these images look like images. Always a good thing. Look at your data. I want to look at the last one, not the first one. The first one's probably fine. Oh yeah, it's clearly something. Was it a 5 and a 3? 5 and a something? Hang on. What are the labels? Oh, labels didn't work at all. Oh no. What happened? What happened? Oh no. Alright, so labels didn't work. Why not? Why is labels broken? What is the current choice? It's that? Okay. What is this? That's 3 and 5. Sure. What about this number? Oh. I see what happened now. Oh no. If you take a look at the first 10 labels, yeah. This is where things went wrong. I want to say labels of I, comma, this row, right? The ith row, which data point we're on. These columns. This cannot be fixed. If you look at labels 11, you'll see that one is empty, right? Because obviously no digit is 11. No digit is the 11. Yeah, let's run this again. That's okay. That's what we're here for. Bang, bang. Again, I'm not sure about this warning. That's suspicious to me. Runtime warning, mean of empty slice. No. That shouldn't be a problem. Oh, do I reset choice? Oh, no. Oh, no. Oh, no. I see what the problem here is. Okay, initially it is trying to take a mean of an empty. Hang on. Labels 0? Yeah. See, I understand this warning now. The initial choice object contains nothing. For some reason, that doesn't count as being inside choices, right? Because it's a different tuple for some reason. That is curious to me. So what we're going to do instead, we'll make the first choice out here, right? Like that. And we're going to get rid of this tuple nonsense. Don't want that at all. Don't want that there. And we're going to do this like this. So you note, I'm not recreating a new tuple or a new choice here. I do that only once I get inside this loop. So when it first checks this loop, after the first iteration, this will always be true. The first time you check it, because the choice will be whatever it was in the last iteration. But I have to sort of seed choice with whatever initial thing I want it to be. Maybe if you wanted to, you could say, oh, choice equals 1, 2. Whatever you want it to be, doesn't matter. I don't want to force it, so it just is what it is. Let's run that. Unhashable type list. It's not a list, it's a tuple. What's the problem here? What is choice? What is choice? Choice is a list. Oh, narca dark. Okay. I see what happens here. Choice equals. Oh, you know what? Actually, tuple is totally fine. I don't need to turn the tuple into a list anymore. Tuple I can use to index into numpy arrays. Maybe not. Out of bounds raises one size 20. Oh, I screwed something up here. What did I do? What is I? Print I 0 in indices. Oh, it's inside here. Oh. Oh. I see the problem. I'm calling this function. I is changing all the time. No, for I in indices. No, this should be fine. Hang on. Let me try this again. Let me try this again. It should fail again here. There we go. Okay. What is indices? These two objects. Great. What is the length of ty? 60k. Yeah, that's fine. Okay. Out of bounds for axis 1 with size 28. But I'm not pulling from axis. Oh, down here. Down here. Okay. Oh, interesting. Does that not work the way I thought it did? If I do this, that is not the object I thought I got? No, it's not. Oh. Whereas if I said a list of this, you get a different thing. Didn't know that. That's kind of irritating. So I do need a list. Choice equals list of choice. And up here, say choice equals tuple of choice. Oh, bother. Fix that. Come back here. We got 10 minutes left. We'll have a data set before the night is out. Now that I promise. We'll save it as some numpy arrays and carry on. Okay, that's going great. So what I really want to do is turn this into like a giant function. Def. Make data. Boom. Perfect. Data. I want data points. What are the images, the input images, and what are the input labels? Is that all I need? And max it, or maybe 1,000. Do that. Don't need that anymore. Don't need that anymore. Cool. What we do is we return ims, comma, labels. Perfect. So we want to use this to make a validation data set too. That didn't work. Hang on. Son of a gun. Oh, maybe it did work. Yeah, it did. I'm an idiot. What is going on here? Try, choice, return. It's like the first line is not getting used. Yeah, I don't know why sometimes this tmux just doesn't want to work. I don't know what the frack happened here. Make data. Alright, make data is right there. It's got the correct things. Alright, fine. Maybe it's fine. Okay. So, I want to make my training train data, comma, no, train images, right? Comma, train labels. Equals make data. Whatever the heck I just needed, end data. So look at that. What do I want? 2 to the 16 data points. And I'll put in tx and ty. Let's do that. Takes a little bit of time, but that's fine. I don't care. And I got my validation, which is going to be different. What did I actually call my validation? Did I? No, I didn't, because I'm a terrible person. Let's come back up here. Do this. D. These are with valid. Valid. Not valid. Valid. There we go. Cool. Data is, of course, looks the same way. Okay, groovy. But not tx and ty. Vx and vy. So we're making our validation data in the same fashion. I don't want 2 to the 16 of these things, though. Jeez, oh man. Like 2 to the 12? No. 2 to the 13. Right. Yeah. So like 1/8 is big. Right? Because that times 8 is 2 to the 16. Hey, great. Perfect. So fewer data points. Dunk, perfect. Got all these things, great. Let me look at some of our... Yeah, let me look at the first data point. What is this, like a 9 and a 4? I don't even know, man. It's like you sort of get some sense that some things belong together. But man, I'm not sure at all. All right, we got 5 minutes. 5 minutes remaining. Let me look at the label for that one. This is hard for a human being to do. Oh, it was a 1 and a 9. Excuse me. Let me look at that again. Does the 9 do this and the 1 does this? What? What? I'm not convinced here. Or is the 1 this one and the 9 is this nonsense? Let's look at that one. Let's look at one more. You know, we might have screwed something up. Oh boy. Oh boy, that's a mess. That's probably a 2 is in there. Maybe a 1? Maybe a 4 even? Yeah. Okay, there's a 2 for sure. 3, 4, 5, 6. 2 and a 6. Okay, yeah, I see the 6 now. Yeah, 6 is right here. So 2 and 6. This is hard. This is real hard. Like, if we get it better than random, you know, then we declare victory. And we say, yes, that was exactly what we wanted. That was exactly what we meant to do, of course. All right, now, with 4 minutes remaining, we're going to try to make a dopey, absolutely dopey model to just do the simplest of things. I do not want this functional model. That's going to that's going to be terrible. I don't want that at all. We'll use TensorFlow, because why not? Oh, no, I need to save this stuff, though. We use HDF5, but I just real quickly, I want to do numpy dot save z, right? Save z compress. Perfect. Save. That's not what I wanted. Come on. Nope. There we go. Come on. A little bit more. Save several ways. Save z compressed into a file. I'm going to call that DanDoesData. Digital data. There we go. .mpz. And then all of the arrays. Arrays to save their files. This is not specified on the names. Arrays to be saved with whatever. So I think TM, TLab. No, I should. For nominal savings. TLab, VLab. Let's try that. That should be good. Let's see if we can do that. Not too much data. Right. Branch slash, what is that going to call this? Digits. There we go. Yeah, there you go. So 17 megs compressed. Not too shabby, in all honesty. Okay. We want to very quickly make a model that's just going to break in our face. That's important that I want the model to do terrible, right? I want to say model equals sequential. Cool. Model.add. Dense. How many things do I need to spit out? I need to spit out 10 numbers, true, false, right? It is not going to be categorical cross entropy. It's now going to be binary cross entropy, I believe. I might be screwing this up. Input shape is equal to 28 by 28. Oh, shoot. That's going to make this not so good, not so good. No, 784. 28 times 28. Right? Like that. Let's do that. We do that? Oh boy. Binary cross entropy is not defined. Oh, SGD is not defined. Yeah. Oh, because it didn't do this. Of course. There we go. That's all fine. What we need to do, however, is reshape our data. Our training input dot reshape of -1, 784. That many features, right? Yeah, there we go. And our output data, TLab, it just is what it is. Oh, hang on. And our validation data, of course, is vimages.reshape, same problem. And I only have to do this reshaping stuff because the input is like a 2-dimensional, but I'm just looking at a 1-dimensional solution right now, just to get something out the door. Okay, we compiled our model. Let's see if this crashes and burns in our face. Look at that, it does something. Even got accuracy? I'm not sure what that's about. Actually peaks at 80%. Well, that's interesting. Not sure what that's about. Well, there you go. Maybe it's perfect. Maybe it's... I'll have to sort it out exactly. What the heck's gone wrong in my model that has binary cross entry? Oh, it's not. Oh, no. We didn't put an activation on it. It's purely linear. Oh, well. You know, it is what it is, right? Purely linear model right here. Even linear activation can be anything. I don't even want to look at it. I don't even want to look at what we're dealing with here, right? Except I do, because I love looking at a train wreck. Look at that. I want to do one thing. We'll look at this. Plot.imshow. We always do imshow. Oh my, that's a lot. That's real deep. Yeah, that's not super informative when I look at that way there. Oh well. All right. We will look at this another time. Thank you all for watching. That was another episode of DanDoesData. But hey, we have a data set now. If we need to make a new one, we can make a new one. We discover problems, we'll discover problems, whatever. But we have a data set. I'll try to upload this script to a new Git repository, and I'll try to link that in the YouTube and everything like that. But until then, I will see you guys next week, and stay safe in the data mines.